Welcome back. So up to this point, we've pretty much deal with static situations where we've gone ahead and said our capacitor is fully charged, for example. In reality, things don't happen instantly, and so it is fast. And for a lot of time, a lot of applications, we can just assume, oh well, okay, within milliseconds after I turn the power on, everything's in a steady state and it's all stable. There is an example of a class of circuits where that's definitely not true, and that's called the RC circuit. And it's not a creative name, it just means I have a resistor and a capacitor in the circuit together in series. And if you think about what's happening with that, the capacitor is building up charge, it's storing charge. Well, that can't happen instantly. That charge has to flow onto it. And we did something similar to this when we derived the equation for the energy of the capacitor. We took just a little bit of charge, and then that added the work more and more and more. So it takes the bigger the capacitor, well, the longer it's going to take for that thing to charge. Putting a resistor in the circuit, though, can dramatically slow things down because, as you know, a resistor is going to decrease the current that's flowing everywhere in a circuit. Well, the current is just how much charge per second we're getting. So the two of those components together then give us the ability to control how long a circuit charges. And that's going to give us a lot of very useful applications. So let's get your RC circuit notes out. This is not a calculus class. I'm not going to ask you to go through the derivation yourself. I'm going to pretty much walk you through it, but it's important that you understand each step. Don't just fast forward through the video and get to the end. This is the kind of thing you're going to be doing from here on out, because in your career, especially because in reality, things are not in a steady state. All right, so let's get started. Okay, so as you can see on the first page here, this is what an RC circuit is going to look like. Let me go to my pen. And you see that we have a resistor and a capacitor. Simple as that. The voltage source is not providing any current as long as this switch is open. Once we close that switch, then the charging process we're going to start. And the larger this resistor, the longer it's going to take for it to charge. And that should make sense. This resistor is controlling the current, just as we were saying. So the capacitor then is storing the charge, and that's building up over time. So by its very nature, we have a time varying system. So we're going to have to look at how to integrate that over time so that we can see what kind of equation it's going to take, and how, most importantly, how long is it going to take for this circuit to charge. All right, so let's go to the next step. Let's see, we will delete this one. So come up to scenario 1. And we want to see how we can figure out an expression for the potential, the electric potential of the capacitor as a function of time. We could look at the current, we could look at the charge, we could look at anything we want. Let's go ahead and look at the potential. And you should see that even though the potential of the battery is constant, it stays the same. Before that switch is opened, before the switch right here is open, the charge on the capacitor is 0, which means that its potential for the capacitor is also 0. So obviously that's not going to be the case as it gains charge. So as the charge goes up, the potential is also going to go up. And since potential is something we can measure fairly easily, that's something that we'll use to track things. Charge is very difficult to measure. On the other hand, to measure electric potential, just a voltage. You take your multimeter, you stick it in there, and you've got it. Okay, so that's why we've chosen to track the voltage. Just remember that you can track anything with that. All right, so when we're looking at the design, and I mentioned here that sometimes the professor will put a derivation on the board and you're going, well, okay, that's great, but I would have never come up with that on my own. And that's okay. A lot of times the theoretical physicists, what they're doing is they're just playing around with stuff with equations until they figure out something that's going to give them the interesting result. And then they present it as though they had thought about it in a nice linear fashion, when in fact they didn't. So part of your job here is really just gaining that experience and to see how these things are typically done. That way, when you're in your own task and you've got your own job that you're trying to figure out how to solve, then you'll know how to draw back on these techniques for that. Okay, so what expressions have we learned that involve the potential difference? Look at step 2, our design. And we're just going to make some notes here because this just gives us an idea of what we can do and what kind of tools we have available. So just, kind of go through your flip book and let's think. Well, obviously the loop rule. So Kirchhoff's loop rule definitely uses voltages. So that's one thing we could use. We need to find an expression for the current in terms of, that's for the loop rule. We're going to need an expression for the current in terms of the charge or the capacitance. right? And the charge, of course, is going to be the current as well. So, or we can get it in terms of the voltage. So that might be the definition of capacitance. So, for example, our C is going to be our Q over V. So that might also be a good place to start. And really, this is how it's done. You just sit there and you go through, okay, what do I know? What do I have available? And see if you can find something that you're going to be able to put together and see your path ahead. All right. So let's go to the formal part for step 3 then. And let's talk about what we've got. So we have a battery voltage. Which we'll call V. Now, we don't have numbers for these because we're looking for an expression, but that's not an unknown. Right? So this is the constant, that battery voltage is a constant. We have our resistor in the circuit. I'm going to draw our circuit over here just to remind us what's going on. And there's our resistor, and then we have a capacitor. Very, very simple circuit. So that's R, and that's C. All right, so this is the resistor, and that's obviously going to be in ohms. And I'm going to have the capacitance, which we'll call C. And we measure that in farads. Okay. Some other things we might have the current, and that, of course, is going to be in amps. We'll go ahead and write out the word. So the current is going to be measured in amps. Make sure that you're converting. If you've got something in milliamps, don't forget to convert to amps. We need that. And then we're going to use a lowercase v, which I'm going to put with one little flag there, to represent the voltage across the capacitor. And that's something that's going to be changing in time. So this would be my V, but across the capacitor, I'm going to have a lowercase v, a little v. And then the charge across that capacitor, we'll put the letters over here to kind of keep them separate. We'll call Q. Makes sense. That's just the charge that's building up over time on that capacitor. And then finally, since we want to know how long it takes, we're obviously going to need the time, T. And we'll measure that in seconds. And charge, of course, is going to be in coulombs. All right, so now we're going to be looking at equations. Well, all right, I'm going to make a note to myself that I'm going to use the loop rules. There's only one loop rule here to use. And so I could very easily go straight to it. I've written it out for you down here at the bottom. But right now, let's just kind of summarize what we have. The other thing we might need is the definition of the current. And the reason why that comes to mind is I need some sort of time variation. Up to this point, we haven't really talked about anything varying in time. Yet what's making this circuit vary in time is the fact that there is a current. And so it's carrying charge that's building up on the capacitor over time. So our definition of current, you can go through your flip books and make sure that you follow along with this, is simply going to be dq dt. We are going to have to use the instantaneous current because it makes sense. It's going to be changing over time as it builds up. And then we already mentioned that we're going to use the definition of capacitance. So our definition of capacitance then is C is going to be Q over lowercase v. Very important that I'm using the correct symbols. If I used a capital V, well, that's not changing, is it? And that's going to make me get quite confused in what's going on. So be very careful with your symbology here. Okay, so step 5 then, let's put it all together and let's get going. So when we cross a resistor in the direction of the electron flow, so remember that, let's just switch to red so we can see that. Our electrons are going this way. My capacitance is providing a voltage. So this might be kind of a new thing to think about. Up to this point, we've only considered a battery to be a voltage source. But remember that capacitor can store charge well. It can just act like a battery. It's kind of an odd battery because it's not a constant voltage, but it's something that we can consider to be a voltage for Kirchhoff's loop rules. So I need to know which plate of this is going to be positive because that's going to determine my sign. So let's think about that for a minute. Here's the negative end of the battery. Then this must be the negative end of the capacitor, and this must be the positive end of the capacitor. See if you can convince yourself that that must be true. So as I cross this capacitor from negative to positive, that means it's going to have a positive voltage. And then I'm going around the loop this way, so I'm crossing the resistor in the direction of the current, of the electrons. So the voltage here for the across the resistor is simply going to be the current times the resistor. And I use my subscript R there just so that I know, I've got lots of voltages going on here. I won't need that voltage anymore. I'm simply going to substitute in with Ohm's law as we've always done. So we've written that down here. And that's all that is Kirchhoff's loop rule. Coming back through the battery, just to make sure that you're cool with that, we're crossing from the positive to the negative, so that definitely has to be negative when we've done that kind of thing before. Okay, so now we want to know about the charge building up, so we said, okay, that's going to have to be the definition of the current here. That's charge over time. That's charge building up. And we say that now we've got that time factor that we need. So since I can't easily measure the charge, I want it to only depend upon the things I can measure: the voltage, the resistance, and the capacitance. So here is our definition that we've decided we were going to use, and I'm going to solve that for charge so that I can get rid of it. That's a good rule of thumb. Anytime you need to get rid of something, take an equation and solve for it. And then when you plug in for it, of course, it'll be gone. So we've got this expression right here where Q is equal to the capacitance times that little v, which is going to be the voltage across the capacitor. All right, so let's look at the next one. We'll just move this out of the way temporarily. So now we'll take that and we'll substitute in. And so this was my original definition of current. And then you can see that I have put in my CV. Let's zoom in on that just a little bit. Get the camera back. There we go. Let's see if I can unselect that. Yeah, let's go to pen. Okay. So now the capacitance is a constant. Can you tell me why? Well, that's because the capacitance is determined by the geometry of the capacitor. So that's going to be epsilon naught times the area divided by the plate separation. Well, none of those are changing, not even with time. So the capacitance is a pure constant. It's printed on the capacitor. So I can pull that outside of my integral. And now I'm left with this. All right, so my whole point of that was now I have I, so I can get rid of that current. So let's take that and let's substitute that back in. And I get, this is the Kirchhoff's loop rule. Some people call this Kirchhoff's voltage law, KVL, you do you. And so I've replaced for the I, and this is my I. See if that makes sense. Okay. I've written it this way because this constant RC is going to be important later on. And it is a constant, right? Because the resistor isn't changing, the capacitance isn't changing. So that's a pure constant. All right. So in order to integrate, as I say, as you know, we have to get all of our differentials. We can only have one differential on each side, and I have to have it in the numerator. So that's going to be important. So let's take this expression then, and let's go ahead and let's separate them. So I'm going to put first I'll put my voltages. Look at my pen back. There we go. I'm going to get my voltages and I'm going to put them on one side so that I can multiply by the dt here. And that's what I've done on this side. So then RC, of course, is a constant. I could put it on either side. It doesn't actually matter. However, this is the part that I'm going to want to integrate. Now you may say, well, wait a minute, Dr. K, why do I have that capital V in there? That's a constant, right? It doesn't depend upon little v. That's true, but it's locked in this expression here. And so what I'll do then, rather than having two time integrals, which I can't have, I'm going to divide that out. So I've got my v's over here. See if that makes sense. Some people may say, oh, well, I'll just have something maybe that looks like this. But that's got to be equal to this single. That's got to be equal to this single integral over there. And I can't do that. That's not going to work for me. So I'm going to leave it together then and divide it to the other side. Now, I want to stress, I could have my RC up here. But for reasons you're going to see in just a minute, it's a constant. It's going to be easier to just pull it out over here. All right. Now, I need to integrate both sides of this equation. Now, the dt side should be pretty easy, right? So if I'm going to integrate both of these, this side is just going to be 1 over RC times the time from 0 to t to whatever time I'm talking about. So remember, my limits of integration are going to be 0 to t here. So that side's quite easy. And like I said, if you don't see that that's easy, then okay, you're thinking too hard. Take it easy. Take it back and look. Integrating the other side is quite a bit more complicated. And so what you will often do in the real world is you'll punch this into Mathematica or into any of a number of software packages where it'll actually solve that integral for you. And you can do that right now. It's probably worth doing. Wolfram Alpha is the successor to Mathematica. It's one of the best things. It's got natural language programming. It's highly worth it. And so you could type in integrate dv over capital V minus v. And it will say, oh, I'm going to assume that capital V is a constant, and it'll work out the answer, and you're done. And it will take seconds. Your boss does not want you spending time manually doing an integration just to prove that you can. And while that might be blasphemy in a lot of physics classes, it's still true. And now, if you're a theoretical physicist, well, okay, yeah, this is your tools to be able to know how to do these integrals, because oftentimes you don't know what the integral is going to be. But here, I already know what I want, so there's no reason not to go ahead and just put it in there. That said, we're going to go through the steps with this derivation so that you can see how it's done. But this is probably one of the last times we'll go through all the steps of the derivation. All right, so I've got this term with this v minus v in there. And if you remember from calculus, the easy way to do that is going to be to do my u substitution. And this is the best u substitution. So now I need to get d. So this, let's copy down our integral down here so that we've got it, since it's going to scroll off the screen. That's v minus lowercase v. Now, this is simply, the bottom part is simply going to become u. So that's going to go to dv over u, which is going to be nice and easy to integrate, except I have to have a du. So to get a du, all you have to do, if you don't remember this, you can go back and review it, but all you need to do is just take the derivative of our expression. So here's my expression. I'm going to take the derivative of both sides. Well, the derivative of u is just du. The derivative of v is a constant. It goes away. The derivative of negative v is negative 1 times v, so that's going to, negative 1's a constant, and so that gives me negative dv. So that right there then is going to be my dv. So that makes my integral now minus du over u. Think about why that's true. I want to solve for dv, so that's going to be minus du. Now that integral is quite a bit easier to solve. Let's pull this aside then. And maybe you recognize this. Maybe you've almost certainly done this one in calculus. You may not remember, but you've certainly done it before. So here's what I've got, what I'm left with. I go through my integral and I have this equation. And what you can see here, the t over the rc, okay, that's where I just integrated the time. That was easy. We didn't have a problem with it. This is taking the integral of both sides here. I took the integral of this side. Now I need to take the integral of this side. I should probably have an integral sign there. And the integral of 1 over u is log u. And you see how that is. No, don't forget, I'm going to have this constant of integration. Never, never, never forget the constant, because it matters here. So I need to set some initial conditions so that I can find that constant of integration. Well, the most obvious thing is at t equals 0, my voltage on the capacitor is 0. We know that because we haven't pulled the switch yet. So let's do that. But remember that this is log of u, not log of v. So what I need to do is I need to find out what u is when v is 0. So if you just put a 0 in for this, you're going to get it wrong. So make sure that you're going back and going through all the steps of u substitution. So that's what we show you here. So this is my u. And so I'm going to put in 0 for v at that time. Well, then I'm simply left with this. So at time 0, u must equal v, not 0. So I'm not going to have a 0 for k. I want this side to be 0, right? So I would have log u plus k is going to be equal to 0 because I've got time 0. But now I know that at time 0, I must have what we have down here. I'll have, let me go back to pencil. So I'll have log v, which was my u, at time t. So that's a constant, as it should be, at time t equals 0. Solving for k then tells me that this is my constant of integration. So if you had forgotten to do that, you would get a very, very wrong answer. So always be careful about your constant of integrations. Don't just blow them off. They're very important. All right, so now we substitute that back into our expression. And what I've done here is I've gone ahead and changed my u back into v minus v, since that's the only place that was left. So remember that u substitution is just a tool. It's just something to get you where you want to be, and then you translate back out into the units that you actually want. All right, now we need to solve that final expression to get v. Now, if you don't remember the rules for logs, be sure and just look them up. But if I subtract the logs, that's the same as dividing. So subtracting 2 logs here is the same as dividing their arguments. So I'll have log of v minus little v over capital V. So if I want to get rid of the log, I need to take e to both sides. E just cancels out the log, and I'm left with what was in here. And so I'm left with e to the minus 1 over RC. All right, we're going to pretty this up just a little bit. Multiply both sides. We're going to multiply it through by v, and that gives me this part right here. So the v goes away, and then I get a v in front. So then finally, I want v by itself, little v, because that's the part that's varying as a function of time. That's the voltage of the capacitor as a function of time. And so I'm going to subtract my capital V and put it over here. Get rid of the negative sign here, and this is my final expression. Now, I can clean that up a little bit because I could factor out this V here. So let's go ahead and do that, and this is what I'll be left with. These two expressions are equivalent. You should be able to see that. Okay, so what this shows then is that the capacitor is charging at an exponential rate. And that makes sense if you think about it, because I've got a little bit of charge, and then more and more and more and more. And so the voltage is increasing exponentially at that point. So I start with my base voltage, which of course is the voltage of the battery. We've already decided that. And then this is T over 1 over RC. RC then, we call RC the time constant, because that time constant controls how fast this exponential is going to go. After a long, long, long period of time, though, what's going to happen? Let's think about that. So let's put this to the side again. So we now have our final expression, and I'm going to copy it down here again so that we have it. And so that's little v, which if it makes you more comfortable to write that as a function of time, that's fine. But it's implicitly a function of time, so I'm not going to get my knickers in a twist over that. And that's going to be v times 1 minus e to the minus t over RC. That is the time-varying voltage for an RC circuit. Simple as that. Okay, so what I want to know then is, how long will it take for the capacitor to reach full charge? How long will it take for little v to finally be big V? So what you want to do then is you want to just change. Let's switch to red so we don't miss our form. You're going to switch so that little v is actually equal to v, and plug that in right here. And then I want you to solve for it. Pause the video. Let's see what you can do. Did you actually pause the video? Because there's something important here. All right, well, let's do it. So make sure I'm on the same page you are in my notes. Here we go. So I'm going to solve this. So I get v equals v times 1 minus e to the minus t over RC. Well, okay, these can cancel, and so I'm left with 1 equals, whoops, I wiped it. Let's try it again. So I've got capital V is equal to capital V 1 minus e to the minus t over RC. And now these cancel, and so I'll be left with 1 equals 1 minus e to the minus t over RC. Subtract that out, and I get 0 is equal to e to the minus t over RC. Now, just to make sure that everybody's cool, if I have a negative sign here, that means it's 1 over that. So minus, it's going to be minus 1 over e to the t RC. I feel like I dropped a minus sign somewhere, did I? Oh, right. I can always divide through by -1. Because traditionally, we're going to write this as, let's put it over here, 0 equals e to the minus t over rc. Do you see that these two things are the same? I just divide through by -1, and 0 divided by -1 is still 0. So either way, though, this is 1 over e to the t over rc. Well, if I'm going to solve this for t, that's going to be a problem, because this won't reach 0 until an infinite amount of time has passed. So once t equals infinity, then I will finally be at full charge. So the reality is that a capacitor never charges. It never charges fully. You would have to wait an infinite amount of time. However, it can be charged for all practical purposes, and that's what we've got down here. So if we wait after 5 of these time constants have passed, so when I've had 5 of these RCs, when t equals 5 of the time constants have passed, I will be at 99% charged. So that's good enough. So we will generally, certainly for the rest of this course, we will consider a capacitor to be fully charged when it's reached 99% of its full charge. And that always occurs at 5 times the time constant. So the bigger the capacitor you have, the longer it's going to take for that to charge to 99%. Makes sense. It's exactly what we said at the beginning. And also, the bigger the resistor you have, the longer it's going to take to charge. Also makes sense, because it's the rate at which I'm charging is slowing down. So that time constant is fundamental to deciding how this circuit is going to operate. So this allows us to figure out what we need. So if I ever want to know that time, I can just put it right in there. Okay. All right. So let's move this aside then. That's what happened to that. Okay. Now, here's where I want you to come in for scenario 2. We want to find the discharge time. And it would be very worth your while to use this as a model that we've just gone through. The steps are basically identical. And see if you can come up with an expression for how long it takes for it to go, starting with a fully charged capacitor with a little v equal to v. It's actually 99% V. And then at time equals 0, how long will it take for the circuit to get down to, for the charge in there to get down to 0? Now, I'm not going to do this one for you. I want you to pause the video and see if you can do it. I know some of you won't. You're in a hurry and you'll say, no, I'll just wait for Dr. K to give it to me. Seriously, take the time. This is some of the best practice you can have for understanding how this system works. Okay. I'm going to delete all of this. Here we go. All right. So I hope that you did it. If not, well, shame on you. Go do it anyway. Let's get my pencil back here. And so you should have gotten a final answer of, oh, that should be a little v. Whoops. My discharge equation then is going to be little v equals capital V e to the minus t over rc. So we're just missing that factor of 1. Instead of 1 minus, it's just going to be v times little v for that. So see if you can get this expression by doing the U substitution and working through all of the integrals. All right, having gone through all of that, now let's see if we can actually use it. So let me zoom out here again. And we'll move this out of our way. And we'll just delete all of these. Get that little sucker out of there. Okay. So a defibrillator circuit is 2 RC circuits. And the way a defibrillator works is it needs to build up a very large amount of charge. Well, when you plug it into the wall, you're just not going to be able to get enough charge to restart a heart. It's just not going to happen. So I can't run that on a battery. I can't have that charge. I need to store a massive amount of charge. So what I do is I have 2 circuits. One is for charging that has a very slow time constant so that I can build a large amount of charge. Then what I do is I flip the switch and I go to a different resistor. And that's what you're seeing here. So this circuit here is the charging circuit. Let me zoom in on that just a little bit so that maybe you can see that a little bit better. So this circuit on the left is the charging circuit. So as soon as I close that switch, I'm going to go through my R1 resistor, which is going to be fairly high. It's going to be a fairly large resistor, so that then I can charge. And I'm only going to go through this circuit. So this would be the battery. This V over here would be the battery, or maybe I'm plugged in the wall or something like that. Once my capacitor is fully charged, then I want to use the discharge equation to dump all that charge very quickly into the defibrillator pad. So when I push that switch on the paddles, then that switch right there closes out. And of course, I can't erase this one, but it closes and everything now dumps through because I have a much smaller resistor here. And so I have a much shorter time constant so that I can dump everything. So we want our defibrillator here to charge to 2,500 volts and 0.15 coulombs. That's a lot. And we're going to have it charge in 5 seconds. But then we want it to discharge in 0.001 seconds. Very quick, just 1 millisecond from that. All right, so well, let's pull this over and let's see what we can do. Now what we don't need to do is rederive anything. You're going to use those two expressions that we found before. So let's write down what we know. So we're going to use our desired voltage and charge. So the voltage and charge we need to choose the capacitor. And that should make sense, right? Because we have C equals Q over V. So if we're given a charge, we're given a voltage, then that's what's going to turn my capacitor. It has to. All right, once the capacitor is known, then I'm going to use the time constant to get what resistor I need. Now, don't forget, the time constant, in order to get to a full charge, I need 5 times that time constant. Very important. So if I want to charge in 5 seconds, then I'm going to have 5 times my time constant. It's going to equal 5 seconds. And you're going to see how that works. So we're going to choose a charging resistor to give a 5-second charge time. And then I'm going to choose a discharge resistor to give a 0.001 second discharge time. So do you see how we're going to approach it? So the known values, then we know that we need the voltage to be 2,500 volts. That's what has to be the potential difference across the capacitor. Obviously, that's not going to be the potential difference across the battery, but we're using that battery to just send charge. And so that potential difference gets bigger and bigger and bigger. Then the amount of charge I'm going to store, we need 0.15 coulombs, which is an, oh my God, huge amount of charge. And I need the time for discharge. So we'll call that T discharge. That needs to be 0.001 seconds. And my time for charging is going to be 5 seconds. What I don't know is the resistor for the discharge, the resistor for charging, and I don't know the capacitor. So those are the 3 things. So our equations are actually going to be very simple. The time constant is 5RC. And then the capacitor design is going to be Q over V. And that's actually all the equations I need. So you may think, oh, I've got to go back to my time constant charging equation. You know, my little v is big V 1 minus e to the minus t over RC, right? But remember, I want the capacitor to be fully charged, and then I want it to be fully discharged. So all I'm really interested in then is the time, because the time to charge has to equal 5RC. Does that make sense? All right, so let's follow our plan, and let's start off by figuring out what our capacitor needs to be. So we are being real, actual engineers here. So I know that, let's switch to pen, there we go. Sometimes whiteboard does not cooperate. There we go. So I know that my capacitor has to be Q over V, and both of these values are known. And so that's going to be 0.15 coulombs divided by 2,500 volts. Go ahead and pause, work it out. I've got it in my notes, so I don't have to go to my calculator. And you'll find that you should be getting 6 times 10 to the minus 5 farads, which is about 60 microfarads, which is a very reasonable value for a capacitor. Most 10 microfarad capacitor is very common. A 100 microfarad capacitor is very common. So this is not an extreme capacitor. This is actually fairly easy to come across. Okay, now my charge time is going to be 5 RC. Well, I know what my charge time is. I now know what my capacitance is. The only thing I don't know is the charging resistor. So I'm going to put a charge here to remind myself that's the charging resistor. So we'll solve that. And so our charge is just going to be T charge divided by 5 times the capacitor. And that's simply going to be 5 seconds. I believe that's what we decided. Yes, 5 seconds divided by 5 times 60 e to the minus 6 farads. And if you work that out, then you should find that, go ahead and pause, work it out, punch it in your calculator, make sure you can do this. Okay, and you're going to find that you need a 16.7 kilo ohm resistor. Now you probably don't have precisely a 16.7 kilo ohm resistor, but you can make one. So you could put in series. We've got 10K resistors in our kits. We've got a 5.1K resistor in our kit, and we've got a 1K resistor in our kit. Well, right there, you've got 16.1. So you need another 500 ohms or so. So take a 220 and a 330. You see that we can just build whatever we need if we need a precise value for that. So the only other thing we need to do is find the resistor that will give us our discharge time. So I've written my charge time equation up here, but the discharge is going to be the same. So my T discharge is also going to be 5 RC because I'm starting from 99% and I'm going all the way down. So we use the exact same thing. T discharge is going to equal 5 RC, and that tells me that our discharge is going to equal T discharge divided by 5C. And this we wanted to discharge in 0.001 seconds. And then again, I've got 5 times 60 e to the minus 6 farads. Both of those are farads. And so work out the math then, and you will find that the discharge resistor should be 3.33 ohms. And then, therefore, we have designed our defibrillator. So as your book points out, you may have made this harder than it needed to be. And that's pretty common. You know, you've done all this work, you've got all this complicated math, and you're like, well, okay, let's use it, right? But we use the math to determine something physical about the world, in particular that time constant. And solving that equation also told us when we would be at our 99% charge, which we're going to consider to be full charge. And so that would tell me how long it would take to get there and how long it would take to drain it when it's done. Now, maybe I needed to know what the charge was at some time. So maybe somebody accidentally pushed the button at 2 seconds instead of 5. Well, okay, then I need to go back to my charging equation and figure out exactly how much charge I have at that point. But that's straightforward. You've got a T, you've got an R, you've got a C, you plug it in, you're going to get your answer. So the lesson here is, even though RC circuits may seem to be complicated, you got to, as long as you're using them for what they're designed for, and you're taking a look at the math and you're really understanding what that math means, then you can usually apply it in a much more simpler case. RC circuits have a very wide application. They're also used in filters, particularly like a low pass filter. And that you've probably seen those in an audio application. So if you've ever listened to a microphone that was directly connected into an amplifier or speaker or whatever, there's a lot of pops and hisses and things like that. Well, that's random noise in the signal. So if I put an RC circuit in between my microphone and my amplifier, then those random variations will get smoothed out, because as the voltage, the signal, increases, it's going to take that capacitor some time to charge. But by the time the capacitor has started to charge, the signal has come back down because it's random from that. Well, the capacitor tries to come back down, and that time is going back up. So only the big changes, your voice, are going to be carried through. The smaller changes, the capacitor just doesn't have time to respond to that. By selecting the proper time constant for that, you can decide what level of frequencies you want to exclude. The higher the time constant, then the less frequencies. You're going to only let the lowest frequencies pass through, which is why we call it a low pass filter. All right, so there's lots of applications to these, and we've really only touched the surface of this. If you take a circuits class later on in your studies, you'll go into a whole lot more detail. But hopefully this is giving you the introduction that you need to understanding what's going on with them. All right, that's all for now. We'll see you next time.